Hey, and welcome back. We're going to be talking about something, again, building off of very important, the definitions of trig functions. Now we're going to see a little bit how to use them just at the start here. So not too much on the length of notes like it was the last time. We'll do more examples and spend more time on that. So here we go. So we're going to keep building on the trig functions that we learned about, but before we do, I wanted to also mention some stuff that I mentioned last time as well, and that is memorizing what sine, cosine, tangent, the big three, are as far as the unit circle in terms of x, y, and r rather than our geometry form in SOHCAHTOA. So remember, sine is always y over r, and so we mentioned the reciprocal function being the ratio that we get out for that specific angle and trig function being x over r if it's cosine, y over r if it's sine, and tangent is y over x. Well, then each one of those big three has a pair with it that is called the reciprocal function. So we have cosecant here as our example, and remember that would just take reciprocal function, for lack of a better term, of sine. We simply just take and do the flipped version of that ratio we call the reciprocal. All right. Now remember, this does give us some issues simply because we can never have an r, a radius length of 0, but we can have x's and y's that are 0. And hopefully you know exactly where. At the quadrantal angles, any one of our axes, the x-axis positive or negative, y-axis positive or negative. So what we can actually do is take these things and rewrite them in alternative forms. So you can see here, instead of just writing sine as y over r and cosecant as r over y, I can actually rewrite sine as 1 over that thing. For example, if I had the number 3, I could actually write 3 as 3 over 1. But if I wanted to do the reciprocal of that, it would have to be 1 over whatever that thing originally was, which in this case would be 3. So same idea here. If I was to take sine over 1, I can rewrite that as the reciprocal flipped as 1 over sine. So you can see the difference being the reciprocal we already had a name for, and that was cosecant. All right. So, and again, it goes hand in hand. You can think of cosecant as 1 over sine or sine as 1 over cosecant because they are indeed reciprocal functions. Okay. Now, don't forget they're saying provided that the angle for whatever we're looking at, in this case sine, is not equal to 0, because if we were to flip that, we cannot have a denominator equal to 0. And that will be one of the most frustrating things that we will deal with in calculus when you guys get there. All right. So I wanted to give you all the reciprocal functions. And again, they each have their own pairing. And so I wanted to kind of highlight that. For sine, we have 1 over cosecant, or for cosecant, we have 1 over sine. And then for cosine, remember we talked about that one being reading it right to left. You can kind of see the COS if you read it right to left, which is secant. So those ones go hand in hand as reciprocal functions, their ratios being flipped. And then, of course, how can we forget tangent? And for tangent, the easiest one of them all, its reciprocal function is cotangent. All right. So again, just more that we need to memorize. There's a lot in this first chapter, definitely, but probably first 3 chapters that you're going to have to spend some time actually memorizing things, and so that you can actually start applying them in chapters 4 through 8. All right. So next thing we're going to look at is where these things are positive versus negative. Now, if we were to write these all in terms of the x, y's, and r's that we know they are, then we would be able to look at which ones are positive. Now notice that for every single one of these, r is positive. It's always going to be greater than 0 and never negative, because it is a length from the origin, the center, out to some other point we call a radius on that circle. All right. But what can change is obviously the x's and y's. And so to kind of streamline this, we're going to make it very simple. We're going to give you a little acronym to help you memorize this. And it is all students text in class. or all students take calculus, all right? Meaning that, again, only focusing on the big three, because the positive negativeness of each one of these reciprocal functions is not going to change. It's just the ratio being flipped. So when we're talking about the positive or negative sign of these things, all of them will be positive here because x, y, and always the r are going to be positive, because that is a positive direction and that is a positive direction to get to anything in quadrant 1. All right. Then they decided to change it to this quadrant 2 here instead of going downwards, because the x-axis is what we started with first. And so they're going to change that to be a negative and then a positive point in this quadrant, which is listed there. All right. And so what will always be positive in that quadrant is sine. Because remember, sine is the y over the r, and everything above the x-axis is positive. So that's why sine is positive here and here. And notice they also list cosecant, and again, that's because it is just the reciprocal of sine. And therefore, the sign of it will not change from positive to negative, just the ratio will be flipped. All right? And so moving along, tangent would be here, and cosine there. And of course, as would be their reciprocal functions, right? So again, just focusing on the big three, everything is positive in quadrant 1, just sine and its reciprocal function in quadrant 2 would be positive. Tangent, because it's y over x, and that would be a negative, and that would be a negative, so negative over negative becomes positive. And then remember, cosine is x over r, so to the right of the y-axis, all of these things are positive. So that's the only one, and of course, its reciprocal function, that would be positive. So there's a nice little chart there for you, but I think memorizing this is a whole lot easier. And you're going to have to be careful when working with these signs here as we progress through and start evaluating different angles for different trig functions. So again, just to make sure that you guys see it all, sine in quadrants 1 and 2, and notice so is its reciprocal function, 1 and 2, right? And then cosine is in 1 and 4 where it's positive. So of course the other ones are negative, I'm not highlighting those. But then remember, its reciprocal function would be secant, so the same places. And then lastly, tangent is in 1 and 3, and therefore its reciprocal function also 1 and 3. So one other thing we want to talk about is that output, right? The output of each one of these functions, and we will go into it much more in chapter 4 when we actually are graphing sines, cosines, tangents, and even their reciprocal functions. But for now, I'm just going to briefly go over it very quickly with you all with one quick example, and that is just talking about sine. Okay, you can do something similar with cosine, but just looking at this circle here, if I was to see what sine and cosine were able to actually give me out, well, remember, sine is always, for any angle, the y over the r. And if we were on the unit circle, which is our favorite of all the circles, because that then makes my r go to a 1, then all we're really focusing on is the y value. And if I was to look at my y value starting at 0 degrees, my y value would be up and down how much? And hopefully you can see 0. We're not up and down any. But as I keep moving around this circle, you can see that as my angle gets bigger, so does my y value. But does it get bigger indefinitely? Not just at that point, but as I keep rotating around the circle, does it keep getting bigger and bigger? Well, hopefully you can see now my y value is getting smaller, all the way back to 0 actually. So we actually start at 0, increase for sine, our output for every angle, until it gets to 90 degrees. That is actually the highest point that we will reach. And of course, since we're on the unit circle, that will be a highest value of 1. And as we increase our angle more to 100 degrees, 120, 145, 170, all the way to 180, it's actually the y value decreasing until we get back to 0 here. And then what does our y value start to do? Well, it starts to get bigger, but in the negative direction. Now we're below the x-axis. So now, not only is our sine value, as our angle continues to increase, our y value is getting bigger again, but it goes all the way to -1, which would be the lowest point we call a minimum. The maximum highest point we got was 1. The minimum lowest point is -1. And of course, we would get everything else in between back to 0. So the way that we can write this, they give it to us in two different forms. One is called the set builder notation, where we're actually telling the set of numbers for y such that the absolute value of y is less than or equal to 1. In other words, I like the interval notation better. We could have anything between -1 and 1, including those values. Okay. Now that goes the same for cosine. Tangent's a little different because it has y and x involved. And that will lead us into the next thing that I'm going to talk about. All right. So again, just wanted to mention this. You should definitely think about this on your own. Maybe even do the unit circle and put some values in, whether it's on your calculator or whatever, and just see what kinds of things you get out. But we will go into this in much more detail in chapter 4 when we're graphing these functions. Okay. So I'm going to go ahead and move on using this circle for a different scenario. All right. So as you can see here, I got two more definitions that I'm going to explain for you all right now. And before I do that, I'm going to go ahead and take this point right here, and I'm going to drop it down straight, remember always with reference to our x-axis, so that we create that right triangle. And again, to get to that point P, I'd have to go right x and up a y value, which I'm not specifying at this moment. And if I was to continue rotating that around, that we call a radius on that circle, and then therefore we're going to call that a length of r. So we do know one formula that we derived a couple of videos ago, and that was x squared plus y squared equals r squared. We call the Pythagorean theorem. But if I wanted to actually take this Pythagorean theorem for this unit circle scenario, where we went over x up y to get to this point with a radius of r, and within that right triangle, I used my Pythagorean theorem to write this equation. What do we know we can do to any equation? And hopefully you know by now in your math career, you can do whatever you want. And if you want to make this look really nice, I would really like this whole thing to be set equal to 1. And in order to do that, what would I have to do to this entire equation? Because remember, we got to do it equally if we want to keep it equal. How would I make r squared become a 1 without changing the r? Because it doesn't have to be a radius of 1, so we like to do things in general. Hopefully you're able to think about it a little bit and come up with, I could just divide by itself. I know anything divided by itself is 1. But remember, to keep it equal, we'd have to do it equally. And that gives me a different look, a not so nice look. But if you notice, since all of this is squared, I could actually write that as x over r quantity squared, the whole thing squared, because that would give me my x and my r squared. Plus, I could do the same thing with the y over r, and that would give me my 1 that I wanted. So it looks a little bit better, but I don't necessarily like the fractions. So what can I replace those with? Does anybody recognize that ratio of x over r or y over r? And I'm not going to wait too long for you to answer because I can't hear you anyways, right? But x over r, hopefully we know, is cosine of this angle we have in there. We'll call theta because that is also unknown. And if I had this whole thing squared, I can write it as cosine theta squared. Plus, Hopefully you also know y over r. If not, start memorizing these. Take the time to memorize it. Trust me, you will thank me later. Y over r, hopefully you know, is sine for that angle that built that triangle x, y, r. And since it's squared, we then have cosine squared plus sine squared equals 1. Now, some people may ask, do we have to put the parentheses? Are those necessary? Yes and no. Yes, if you're going to write it on the outside like that, you have to. Because if you don't write it here, then you are telling me that the angle is actually the thing that's being squared, not the sine theta, that y over r that we originally had. So you have to have the parenthesis there. If not, and you don't want to write it, as I told you, mathematicians, we make up things so that we don't have to write extra things that are unnecessary. So this is what we came up with. Since cosine theta is the thing that I'm squaring, that whole function, that ratio that would come out from that, we're going to put it right after the cosine so that you know that's what's being squared, not the angle. So this is the alternative way to write it, but it actually means the exact same thing as the line above. And because this came from the unit circle on the Pythagorean theorem formula, we actually call this the Pythagorean identity. Now you may be wondering, well, what about tangent? Or what about all the other reciprocal functions? This one is the one that I definitely want to highlight, and I want to make sure that you guys memorize. Because all the other trig functions, all 4 of them, can actually be simply derived by this. All right? So as long as you have this one memorized, you can come up with any of the other ones. All right? But that takes a little bit of work. So I'm also going to talk to you real quick and remind you about what we defined all of these trig functions to be, their ratio. So remember, sine was y over r, therefore r over y for cosecant. Cosine, x over r, and therefore secant was r over x. And then tangent was y over x, and cotangent, therefore x over y. And so one more time, I'm going to focus on the big 3 here, because there's actually a way to rewrite all of the other 4 trig functions in terms of the 2 most important, the ones that we like the best, because they do not have any x's or y's in their denominator. They simply and will only always have the r values. So they just play a whole lot nicer than the other ones. So since I know that tangent is y over x, I can actually rewrite. If you remember up here, we talked about sine on the unit circle. Actually, since this will go to 1, would be y. Well, then cosine, since we know it's x over r, if we let that be 1 again, then we know it would be x. And therefore, if I simply just put y over x, I could also put sine over cosine, since that's what they're equivalent to. And we just said that y over x is tangent. Thus, we can then also say that tangent is equivalent to sine of the same angle over cosine of the same angle, theta. So that's another one that we will utilize. And if tangent is equal to sine over cosine, then what other one should you know immediately? That's right, cotangent. Because remember, cotangent is just the reciprocal, so it's going to be cosine over sine, because that would give us an x over y if we actually substituted and worked that out. Okay, so you can see these Pythagorean identities and these other ones that I just derived with you called quotient identities. And the one I told you have to memorize for this is sine squared plus cosine squared equals 1, which we just derived. Okay, now what about the other ones? Well, don't forget, I just gave you the tangent is sine over cosine, and the cotangent is cosine over sine. Quick little proof there. What about the other 4 trig functions that we have? Well, let's do that real quick using the one that we just derived from the Pythagorean theorem. Cosine squared plus sine squared, which since you're adding, you can switch those as they have here. Well, remember, since this is an equation, I can do whatever I want to it. And if I wanted to take all of those and actually divide, well, remember, we just spoke about tangent being sine over cosine. Well, then I could just divide by cosine squared to that, and there's my tangent. But remember, to keep it equal, I'd have to do it equally to everything. And therefore, I would then have sine squared over cosine squared, which is tangent squared for that angle theta. Plus, then I have a cosine squared theta over cosine squared theta, which anything divided by itself is 1, and it would be equal to 1 over cosine squared, which hopefully you remember that is a reciprocal function of cosine. Therefore, we can write it in a much simpler form as secant. And there's another. So if you wanted to do the same thing, it's pretty simple to get the last. You just take your sine squared theta plus cosine squared theta equals 1. The 1 I told you to memorize. And instead of dividing by cosine squared, like we did here, here, and here for that whole equation, now, you guessed it, we're going to divide everything by sine squared. And then we will simply, pun intended, simplify this, which we know is 1. Remember, cosine over sine is cotangent, and since they're both squared, it will be squared for that angle theta. And then 1 over sine squared would be the reciprocal function for that, which is cosecant squared. And there is our third alternative version. Now remember, this right now is set up to find cosecant squared theta. That's what it's equal to. What if you didn't want that and you wanted the cotangent squared? Well, remember, it's an equation. You can still do whatever you want. So if you wanted just that by itself, then go ahead and subtract the 1 over. And that would cancel that out, and now we'd have cotangent squared theta equals cosecant squared theta minus 1. So there are a lot of different versions of these, which I don't expect you to memorize all of them. If you can memorize all 3 of these, that would be ideal. But as long as you have the sine squared theta plus cosine squared theta equals 1, then you can come up with the other ones pretty quickly. Not as quick as if you had them memorized, but not bad. Again, I've tried to harp to you all. This is a very, very important section, part of the class that if you understand chapters 1, 2, and then 3, you're going to be set to do really, really well for the rest of the class. So I'm trying to overemphasize some of these examples with you. Go ahead and pause it right here and see if you can work this one out, very similar to the previous. All right, hopefully you gave yourself some time to work this out on your own. This time they want us to find sine and cosine, which is pretty nice. And they also made it a little bit simpler and just simply telling us that our angle is in quadrant 2. We didn't have to think about it a whole lot. So when we go to draw this, my x, my y-axis, and then I will draw my angle theta. Now, of course, with that angle, I'm going to drop that straight down to the x-axis so that I have my right triangle. And because they gave me cotangent, that I know is the reciprocal of tangent. And since tangent is y over x, I know cotangent is going to be x over y. I already know that this is going to be a negative direction, this is going to be a positive direction, and our r is always positive. So I also know that the x value that they gave me is going to be what is negative, even though they threw it out in front. The y value is 24, and I can actually look at this and tell you, Even though a lot of you, if you actually did pause it and go try this on your own, you use the Pythagorean identity or you use the Pythagorean theorem. Not me, because I recognize that this is a Pythagorean triple that I had written down for you all a couple sections ago. This is actually a 7, 24, 25. If you ever get a nice number like that, you know it is a Pythagorean triple. If it still has the root we call an irrational number, then it's not nice and it's not worth memorizing. So because of that, I now know and have all three sides, so therefore they can ask me any of the 6 trig functions they want to know. And I should say 5 because they already gave me one. I really wish they asked me for tangent because then we could just do the reciprocal and be done, right? But sine and cosine, we needed the, for sine, y over r. And for cosine, the x over r. And that would be wrong. That would be a mistake that a lot of people would make because they would leave off the negative. So whether you figure it out by the direction for those, or you figure it out because we know we're in quadrant 2 and you write this down. I knew sine was going to be positive and cosine negative. However you do it, don't lose your sign. No pun intended. So that is it, my friends. Keep practicing, keep memorizing as much as you possibly can because it will help you immensely in the future. Until next time, Alan, signing off.